Hello there, Mr. Sutton here with the AB Calculus 6-6 Extra Practice Number 3 solutions on motion and position. For this free response problem, we have a car traveling on a straight road, and the velocity from 0 to 24 seconds is given by this piecewise function in the graph above. First task, we want to find the integral from 0 to 24 of v of t dt, and then say what we just did in terms of real-life context. So let's get the number part of this first. To take the integral of v, I'm basically finding the area under the curve of velocity here. So conveniently, this is just one big trapezoid. We have a base of 24, and up here this is a base of, let's see, from 4 to 20 is 16. So we have 24 plus 16 over 2 times a height of 20. So just finding that trapezoid area. And you don't have to simplify it, but I'm going to. So let's see here. This is going to be 20 over 2 is going to be 10. 12 plus 24 is 36. So 36 times 10 gives us 360. And for the units, since we're taking the integral velocity, we're getting rid of a time unit and just getting meters. So that's 360 meters. So what we just said here is that over the time interval from 0 to 24, and that's going to be 0 to 24 seconds, the car is going to travel 360 meters over the interval from 0 to 24 seconds. For this part of the problem, they want us to find v prime of 4 and also v prime of 20, or say they don't exist. And then also don't forget those units of measure. So for v prime of 4, this is the slope of the v graph. So taking a look up here, we take a look at 4, and we see that at that spot we actually have a corner at time equals 4. So v itself does not have a derivative there. This is a non-differentiable spot. So I'm going to say there is a corner at time 4. Therefore, v prime of 4 does not exist. Next, we wanted to find v prime of 20. So here's time 20 on our graph. Now this is just asking for the slope of this straight line, basically. So to find that, we just need to find the average rate of change from time 16 to time 24, because it's a straight line, so the slope is going to be the derivative. So we've got output value of 0 minus 20 over 24 minus 16. So this is going to be negative 20 over 8, which we could reduce to negative 2.5. And v prime, that's basically the acceleration, so that's going to be meters per second squared. For this part of the problem, we're defining a of t as the car's acceleration. We want, from time 0 to 24, a piecewise defined function for a of t. So remember that a of t is really just the derivative of velocity, basically just the slope of this graph up here. So now that we've defined it this way, we're just going to split this graph up into a piecewise function. So we have this interval from 0 to 4, where we have a certain slope. We're going, let's see, up 20 and over 4. That's going to be a slope of 20 over 4, or 5 over 1. We'll just call it 5. So we've got a slope of 5, just a constant value of 5, if you're on the interval from 0 to 4. Now on the next interval, from 4 to 16, this is just a straight horizontal line, so that's a slope of 0 from 4 to 16. And then on this last one, we actually just found this slope going downhill in part B. You're going down, let's see, down 20 and over 8. That's negative 2.5, or negative 5 halves. And that's going to be on the interval again from 16 to 24. For this last part of the problem, they want the average rate of change of v on the interval from 8 to 20. So let's do that, and then we'll tackle the next part of this question. So that's going to be v of 20 minus v of 8 all over 20 minus 8 for the general setup. For v of 20, that's the velocity at time 20 here. Now that looks to be about 10. If you're not sure, though, remember that this line here had a slope of negative 2.5. So for every step I take to the right, I'm going down 2.5. I'm taking 4 steps to the right if I'm going from 16 to the t-value 20 here. So that's going to be 4 times 2.5 down, which is 10 down. So that is going to be 10 for v of 20. v of 8 is a little bit easier. That's just part of this horizontal line up here, which has a value of 20. So we've got 10 minus 20 over, yeah, I might as well subtract those, over 12. So that's negative 10 over 12, so negative 5 over 6, and this is going to be meters per second squared, because we're, again, basically taking the average rate of change of velocity. So that's the acceleration, average acceleration over that interval. Now the next part of this question, does the mean value theorem guarantee a value of c on 8 to 20 such that v prime of c is equal to this average rate of change? Why or why not? So mean value theorem requires differentiability on the open interval that is in question. So are we differentiable for the v function on the interval from 8 to 20? Well, taking a look at the graph here, we see that we have a corner at time 16. So we are not differentiable across that whole interval. Since v is not differentiable across the whole interval, that means that the mean value theorem does not apply and cannot guarantee what they're asking here. For this free response problem, we have Kathleen skating on a straight track. She starts from rest at the starting line at time 0, and between time 0 and 12, her velocity is measured in, her velocity k is measured in feet per second, is differentiable, it's increasing, and values of k are shown in the table up here. Nice. So for part A here, we want to use the data in this table to estimate Kathleen's acceleration at time 4 with units of measure. Okay, so acceleration is going to be the rate of change of velocity. So if we want to estimate the acceleration, we can't get the instantaneous acceleration, but we can at least get the average acceleration, get the average rate of change of velocity. So we're just going to get the average rate of change then of k on some interval that contains 4. So probably the best interval to use is the interval from 3 to 5. That's the smallest interval containing time 4. So let me just do AROC on 3 to 5. That's going to be k of 5 minus k of 3 all over 5 minus 3. And I'm going to say that acceleration is approximately equal to this because I'm acknowledging that I know this is not going to give me the exact acceleration necessarily. So that's going to be k of 5, which is 10, minus k of 3, which is 5, all over 5 minus 3, which is 2. So we have 5 over 2 essentially. And let's see, since we have feet per second divided by seconds, that's going to be feet per second squared, so negative 5 halves, or positive 5 halves feet per second squared. For this part of the problem, they want us to use a right-Riemann sum with 4 subintervals indicated by the table data to approximate integral from 0 to 12 of k of t dt with units of measure. And then they want to know if that's an over or underestimate for the true value of the integral. So let's get that Riemann sum. I'm going to start by saying integral from 0 to 12 of k of t dt is approximately equal to, and I'm going to get that out of the way just so people know that I'm not giving the exact value. This is an approximation. They want us to miss in a specific way using a right Riemann sum. So I'm going to have 4 basically rectangle areas that I'm adding together, 4 base times height kind of areas. So I've got, for the first interval, I have a rectangle going from 0 to 3, so that's a base of 3, times a height of, well, let's see here. It's a right Riemann sum, so I'm supposed to use the height at the right endpoint of each rectangle. So I need to use the height at 3, which is going to be 5. So base of 3 times a height of 5. Now for the next rectangle, we have a base of 2 going from 3 to 5, times a height of 10. Again, I'm using the right endpoint's output, k of the right endpoint. And then we have a base of 3 times a height of 20, followed by a base of 4 from 8 to 12 times a height of 24. And if we wanted to, we could simplify all of this. But this is a no calculator problem, so be careful doing it. So if I did want to simplify it, it's going to be, let's see here, this is 15 plus 20 is 35, plus 60 is going to be 95, plus this is 96, so we have 95 plus 96. That's going to be 191, and the units on that is going to be feet, since I just did the integral of feet per second. When you take an integral with a time unit, you're basically multiplying by the time unit. So that cancels out my seconds and gives me feet, 191 feet. And now they wanted to know if this over or underestimates the true value of that integral. Well, the key here when you're talking about over or under is whether your original function is increasing or decreasing on the interval you took the integral. So taking a look back at the problem, we said that k was differentiable and increasing on the interval from 0 to 12. Since k is increasing on 0 to 12, that means that a right Riemann sum, RRAM, is going to overestimate. So that means that 191 is going to be greater than the true value of this integral. Again, this is going to be an overestimate because we're doing RRAM on an increasing interval. For this part of the problem, we have a new skater, Nathan, starting 5 feet ahead of Kathleen at time 0. Nathan's velocity is given by this n of t function, which also is measured in feet per second. They want us to write but not evaluate an expression with an integral that gives Nathan's distance from the start line at time 12 seconds. Well, if I want to know where Nathan is at any given time, I need to know two things. First off, I need to know where he started, and I need to know how much his position changed over 12 seconds. So I know where Nathan started. It was 5 feet ahead of Kathleen, 5 feet from the start line. So I can say Nathan's distance equals 10, or 5 rather. Nathan's distance equals 5, that's starting amount. Now to figure out how much his position changed, I have to take his change in position, which is his velocity here, and integrate that over the interval from 0 to 12. That'll give me his total change in position if I integrate the rate of change. So I'm going to add the integral from 0 to 12 of n of t dt, and that's all I need for this one. For this last part of the free response, we want an expression for Nathan's acceleration in terms of t. Now remember, Nathan was introduced in part C with the following velocity formula. So it was n of t equals 150 over t plus 3 minus 50 e to the negative t. So in order to find an expression for Nathan's acceleration, we just need the derivative of his velocity here. So we're going to just do n prime. And before I do that, let me just rewrite this function so it's a little easier to take the derivative of. So I'm going to rewrite this first term in particular as 150 times t plus 3 to the negative 1. And now that'll make it a little bit easier to use my power rule when I take the derivative. So going ahead and taking that derivative, to get a of t, we have n prime of t. I'm just going to spell this out so that people know what I'm doing. So that's going to be, let's see here, negative 150 times t plus 3 to the negative 2. And I would multiply by the derivative of t plus 3, but that's just a derivative of 1, so I don't really have to worry about the chain rule right there. For this next one, though, this is going to be negative 50 e to the negative t times a derivative of negative t, which is negative 1. So altogether, then that becomes positive 50 e to the negative t. And this is my expression for acceleration. Looks like I'm done. For this calculator-based free response problem, we have a particle moving along the x-axis with a velocity given along the interval from 0 to 5 for time by this v of t function here. And we know the particle position is x equals 8 at time 0. Okay, so given that setup, our first task is just to find the acceleration of our particle at time 4. Now, acceleration, remember, is just the derivative of velocity. So if you're looking for a of 4, you're really looking for v prime of 4. And since we're just taking the derivative of a function they already gave us at a specific point, we don't actually have to figure out what the velocity's derivative looks like. I mean, we could take this derivative pretty quickly using the chain rule, but we don't actually have to do it. We just have to use the derivative function on our calculator on this at 4 and give them the answer. So let me do that now. So here I am on the calculator. I've plugged my velocity function into y1 in the y equals. Let me quit out of there now, and I'm just going to take the derivative at 4. So math 8, and then we're going to do dx down there. I'm going to do alpha trace y1 because that's where I stored my velocity function. And we're just going to go over here and put 4 in there. Press enter, and that's about 0.714. Now they didn't give us any units here, so we're just going to say approximately equal to 0.714 and call it a day. And again, the only thing I needed to show before using my calculator was that my acceleration was just the derivative of velocity at 4. For this part, we want to find all times in the open interval 0 to 5 where the particle changes direction, and then during which time intervals does the particle travel to the left. So if I'm looking for a direction change, I'm basically asking where is my velocity, where is v of t changing sign. So we're going to look that up on the calculator. So recall on my calculator here that I put my velocity function in y1. I'm actually just going to graph that now on the interval from 0 to 5. To do that, let me go to Window, and I'll do 0 for x min and 5 for x max, and then let me just do zoom 0, zoom fit, and let's see what this looks like. So there's my velocity function on the interval 0 to 5, and we're crossing the x-axis. It looks like at 1 and 2. Just to be on the safe side, let me go ahead and do second, trace, and then option 2 for zeros. I'm going to find those zeros using the calculator. I'm pretty sure it's 1 and 2, but it's not going to hurt me just to take a look here. So enter once to the left, enter once to the right, enter again. And that first one is indeed at time 1. Now let's do second trace, option 2 again. And let me find this other x-intercept. So enter once to the left, once to the right, enter again. And that one is 2. All right, so we've confirmed it. So there was what I just graphed out, and we see that v of t changes sign at times 1 and 2. So those are the times, therefore, that our particle is changing direction, at times 1 and 2. Now we also wanted to know when the particle is traveling to the left. So that's going to be where the velocity is negative, less than 0. We see that our velocity is less than 0 just on this one interval here between 1 and 2. So therefore, the particle is traveling left on the interval from time 1 to time 2. For this part of the problem, we want to find the position of our particle at time 2. Well, we know the position of the particle at time 0. It's 8. So position at time 2 is going to be the initial position of 8 plus the integral of the derivative of position, which is this v of t function here, from time 0 to time 2. So integral from 0 to 2 of v of t dt. And now we just have to put that in the calculator. So here's what I'm entering in my calculator. I've got 8 plus integral, which I got math 9 to get that, from 0 to 2. I did alpha trace, and then I pulled up y1. That's where I stored my velocity function. I have an x in the dx. Press enter. And that's going to be 8.369 for that position. For this last part of the problem, they want the average speed of the particle over the interval from 0 to 2. So I need to set this up as an average value type of problem. I need 1 over the interval length, so 1 over 2 minus 0, times the integral of the thing I'm trying to average. So that's going to be the integral from 0 to 2 of, and if I want to average speed, well, speed is just the absolute value of velocity. So I'm going to have to do absolute value of v of t dt inside there. And the rest of this is just calculator stuff. So doing this on the calculator, let me set up my fraction. Let me do alpha y equals n over d. And I've got 1 over 2 minus 0, which I guess I could just write 2. But hey, we're here now. And now I need an integral, so math 9. I'm going from 0 to 2 on this. And I need absolute value of velocity. So how do I get that on the calculator? Well, let me do, let's see, alpha, and then this this window menu here. Absolute value is option 1, so let me press enter. And then let me do alpha trace. That gives me my y equals menu. y1 is where I stored velocity, so let me press enter to get that in there. And then I'm just going to do dx, press enter, hope for the best. And that's about 0.371 for the average speed.